really, 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 really miss you guys. We're going to continue on with resonance, and I want to talk before you do your Lewis structures, and before you have your pretzel and M&M or pretzel and red hot time, then I want to go through expanded octets versus things that may have fewer than a fulfilled octet, and what elements specifically we may see with that. And I'm pretty sure we left off with this resonance. I sure hope so. Today you have a really, really, really busy booked day. So at the beginning here, you're watching this. I'm going to try to make this as fast as possible because my phone is about to die, but I want to make sure that we get this content in before you do your Lewis structures. After you finish the video, we're going to have you're going to do a Lewis structure activity. You're going to get with a partner, and Annie's going to break you up into partners. And then you'll model each of those using your pretzels and M&Ms, and then you'll agree on that for your worksheet with your partner. So there is a front and a back. If there's resonance structures on any of them, please make sure that you draw the resonance structures. Annie's going to go around and make sure that everybody is doing fine and doesn't have any questions, because Annie's a pro at this. And then after you get that done, when all of the groups are done, Annie's going to break you up into larger groups, and then she's going to pass out a new paper, and each of the larger groups is going to have a particular set of Lewis structures that I want you to work on together. After you've done that, then you're going to have your pre-lab and your lab write-up that Annie is going to pass out to you as well, and you're going to have the rest of the class time to write out your introductory procedure and your guided inquiry procedure, as well as answering any pre-lab questions. So whatever you don't get done with that is going to be homework. You are also going to have homework on electronegativity values, and then finishing up those covalent bonds, because I kind of skipped some slides there, and I was wanting to do it tonight, but I don't think my phone is going to have enough juice to do that. So I'm going to make a small video tomorrow morning, so that way that will be posted on your blog. And then if time allows, then play that video. If you all get done with all of that stuff before the bell rings, play that video, and then that way you won't have homework then either. Okay, so I'll try to make that tomorrow morning whenever I come in. Also, Annie is going to pass out to you an electronegativity table, so then that way you can have that for the video. So Annie, if you would pass that out now, it's the very top paper that's on the stack of the AP Chem papers. Those electronegativity values I'll explain a little bit more in your video for homework, but you're not going to get anything like this on the AP Chemistry test, and I doubt that they'll be embedded in questions either. This is just kind of a general conceptual thing to know. I would highly suggest that you know hydrogen's electronegativity, as well as then boron, carbon, nitrogen, oxygen, and fluorine. Let me repeat those again. I would know hydrogen, boron, carbon, nitrogen, oxygen, and fluorine. And the really nice thing is that boron through fluorine all go up by an increment of 0.5. So fluorine is 4.0, oxygen's 3.5, nitrogen's 3.0, carbon's 2.5, and boron's 2.0. So it's really nice that they have that trend, but those are usually very common ones. And then also chlorine is 3.0. That would be another one that I would just know kind of off the top of your heads. Okay, and I may ask you those. And then hydrogen is 2.1, just if you wanted to know, but you already have your paper probably now. Okay, resonance. So we said that resonance is more something that we see in nature, and ultimately resonance is where I could draw a Lewis structure in more than one different type of light. So we looked at ozone. Let's actually go back. Here's ozone. So I'm looking at ozone, and I see that there's a double bond on one side and a single bond on the other. I don't have to always draw it this way. I can draw it this way as well. I could draw it with the single bond first and then the double bond on the right side. So in nature, we don't find this one sometimes and this one other times, or this one 50% and this one 50%. I actually find a mixture of the two. So when we see ozone, we actually find that the electrons are more spread out or evenly distributed around that central oxygen versus it being double bond solely on one side and a single bond solely on the other side. So we have to draw resonance structures because this is how we show that it's actually a configuration of all of these types of structures. So again, we said last time, let's assume that maybe I'm thinking of like one ozone to be like blue, the other ozone to be represented by yellow. And really what I'm getting then is a mixture of the two, or a synthesis. That's such a T. Hicks word there, love it. And we're getting a synthesis of green, okay? Let's go to this. You're going to be doing a lot of these, so I'm going to skip over this because you're going to be doing tons of these Lewis structures today. So in truth, let's just say, actually, wait, this is my formate ion. Okay, so on the last slide, it says draw the resonance structures for the formate ion, HCO2 minus. And this is these are the resonance structures for the formate ion. So I can see that formate has a single bond and a double bond for oxygen. So the double bond could go here, or the double bond could go here. So that's why we have resonance structures. So it says that in truth, electrons that form the second carbon-oxygen bond in the double bonds below do not always sit between that carbon and oxygen. That means because resonance is happening based on here, remember that really the electrons are going to be evenly distributed around this carbon and these oxygens. So it's not just going to be a double bond and a single bond here, rather than there's going to be electrons that are just going to be floating in between around here. So we call these electrons localized electrons, or I'm sorry, they're not localized, we call them delocalized electrons. Delocalized electrons have the ability then to move around. They are not stuck in one particular place. So resonance structures have delocalized electrons, meaning that the electrons can be distributed from these outermost atoms to that central atom. Okay, so they're delocalized. And metallic bonds are another thing that we'll see with delocalized electrons. So that would be a really good, I think, other example of what delocalized electrons would behave like. So in metallic bonds, we know that electrons move around in an electron sea because they are not stuck or localized to one particular cation. Instead, they are attracted to multiple cations, multiple of those metals, and that's what causes that sea of electrons. So they're delocalized electrons. This would be an example of benzene. So the organic compound benzene, which is its chemical formula is C6H6, has two resonance structures. And if we look at this, this would be an example of a cyclical or a cyclic or aromatic organic compound. I have a double bond here, here, and here. Or I could just alternate those double bonds. Oh man, sorry guys, phone doesn't have much battery. Okay, so I could also just alternate those double bonds like I see in this one. So we have resonance also in organic compounds. Oftentimes in organic chemistry, we draw cyclic compounds like this. We kind of forget about the hydrogens. We just assume that we know that the hydrogens are there. And each point here that I see would be a carbon. So I have a carbon here, 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 and here, all in the corners. Oftentimes, instead of drawing benzene like one of these, because it doesn't matter, I could show that the double bond could go either way, we usually just draw benzene like this, a circle in the middle of that particular cyclic structure. And we do that because it's showing that the electrons are delocalized. They can move around wherever they want among all of the carbons. So oftentimes that's how we'll show, especially with an organic aromatic compound like that, we show delocalized electrons or resonance structures with just a ring. Guys, on this question it says, would you expect hexatriene to have multiple resonance structures? If not, why is this molecule different from benzene with respect to resonance? So do we expect hexatriene to have multiple resonance structures? Tell me why, or tell me why not. I'm actually going to let you sit on this, talk about it, take like a couple minutes to talk about it, pause the video, I'll wait for you to pause the video. But pause the video so then that way you can come up with an answer. And then I want you to post that answer. I want somebody to get on their phone and post that answer on the blog. And then I'm going to have my phone by me so then that way I can tell you if you're right or wrong, okay? So post the answer on the blog and then I'll tell you if you're right or wrong and then I'll explain. So post the answer and give me an explanation because it says, if not, why is this molecule different from benzene with respect to resonance?